Welcome students. In this video lecture we are going to learn how to solve a one-dimensional wave equation where initial velocity is given. So let us see a problem here. Look at this one. A string of length L with fixed ends is initially at rest in its equilibrium position. If it is set vibrating by giving each point a velocity, a function is given. Evaluate the displacement of the string. This is the problem. Now let us see how to solve this. As usual, first let us write the one-dimensional wave equation, which is dou squared y by dou t squared equal to a squared into dou squared y by dou x squared, where y represents the displacement and x is the distance and t is the time. And the next, let us write the correct solution of the equation, which is y of x comma t is c1 cos px plus c2 sin px into c3 cos pat plus c4 sin pat. And this is the picture of the string given because the string is having length L with the fixed ends. So the two ends x equal to 0 and x equal to L are fixed. Thus we have the first two boundary conditions as y of 0 comma t 0, y of L comma t 0, because already we had discussed this in last class itself. When x equal to 0 at this point, this end is fixed. Fixed in the sense there will not be any displacement at this end. So displacement means y. So at x equal to 0, y will be 0. So remember, y is a function of x and t. So when x is 0, there is no displacement. So we have y of 0 comma t equal to 0. Similarly, when x is L at the other end of the string also, there is no displacement. So y is 0 when x equal to L. So that's why you have the second condition, y of L comma t equal to 0. And the third is about initial displacement and the last is about initial velocity. So let us see how we get the answers for these. Look at the problem again. A string of length L with fixed ends is initially at rest in its equilibrium position. So initially the string is in its equilibrium position. So equilibrium position means the displacement will be 0 initially. Initially the displacement is 0. So what is the displacement? Y. And it is 0 initially. What is the meaning of that? Initial displacement is 0. So displacement is y and the word initial means time 0. So when t is 0, y will be 0. So that's why we get the third boundary condition. And let us see how we get the last one. If it is set vibrating by giving each point a velocity. So this velocity will be the starting velocity because before starting the vibrations, they are setting this as the starting velocity for the string. So this is the initial velocity. That's why we have written here dou y by dou t at x equal to 0 because velocity means rate of change of displacement. Since y is the displacement, dou y by dou t is the rate of change of displacement that denotes the velocity. Since it is initial, we write x comma 0. The word initial means at time t equal to 0. This is given by the velocity v. Actually, this is the function given here. Now let us apply these boundary conditions one by one. Take the first one, y of 0 comma t 0. So first let us apply the first boundary condition, y of 0 comma t 0. So what is y of x comma t? This is the correct solution. In that, put x equal to 0. So put x equal to 0, you get y of 0 comma t. When we put x equal to 0 here, cos 0 1, sin 0 will be 0. So the answer of this term will be C1. And the next term is having t. We are not touching that because t is t only. Only x we are making 0. So the answer of the first term is C1 and the second term we just have to write as such. The condition says this is equal to 0. This is equal to 0 and we should not touch or equate any term having variable. This is having variable because t is the variable here. So this is equal to 0 will imply the constant term C1 equal to 0. So this is the first result we get, C1 equal to 0. Now let us apply the second boundary condition, y of L comma t 0. So what is the meaning of y of L comma t 0? We have to put x equal to L. So go to the correct solution. we have written the correct solution here, and in the place of x we have to substitute L. In the place of x we have to substitute L. So here you have, in the place of x when we substitute L, see already C1 is 0, so let us not write the first term, only you will have the second term C2 sin PL. In the place of x we have put L, so C2 sin PL into the second term is as such because there is no change in t, and the condition says this is equal to 0. This is equal to 0, equate that to 0. And again, variable term we should not touch. So what has to be 0? C2 sin PL has to be 0. So either C2 will be 0 or sin PL will be 0. Suppose if you take C2 0, since already C1 is 0, now if you take C2 also 0, what will happen to the correct solution? Look at this correct solution. C1 0 as well as C2 0 means the entire answer will become 0. So y of x comma t will be 0, which is actually known as a trivial solution because whenever the string is at rest, there will not be any displacement. The displacement will be 0. That is actually known as trivial solution, but we need only non-trivial solution. So C2, taking the option C2 0 is not possible. So C2 cannot be 0. Hence we have to take the other option, sin PL 0. And we know sin n pi 0 is a very famous formula. We are aware of this. Sin n pi 0. Now we get sin PL 0. So comparing these two, what we get? PL equal to n pi, or the value of P is n pi by L. Now this is the second result we have got. Now let us apply the third boundary condition. Y of x comma 0 0. Y of x comma 0 0. X comma 0. So what we have to put? We have to put t equal to 0. In the place of t, we have 0. So this is again taking and writing the correct solution. So in this correct solution, we have to put t 0. Where you have t, here you have t. So here you have t. When we put t 0 here, cos 0 1, sin 0 0. So what is the answer of this term? Sin 0 0, cos 0 1. So the answer of this term will be C3. So answer of the second term will be C3 here. And in the first term already C1 was 0. So the first term is having only C2 sin Px into C3 equal to 0. And when we equate this equal to 0, since this is variable term, we should not touch. And already we saw C2 cannot be 0. So now the only possibility is C3 has to be 0. C3 has to be 0. Now we have to proceed to fourth condition. But fourth condition is a non-zero boundary condition. So you can look at here. This is the fourth boundary condition. All the first three boundary conditions are having 0. So we can directly substitute first. But when the fourth boundary condition comes, it's having non-zero in this. So before applying any non-zero boundary condition, we have to generalize the solution. So let us see what is the meaning of generalizing the solution. Now let us take and write the three answers what we have got. First answer was C1 0. Second answer P equal to n pi by L. And third answer C3 0. So we have taken and written all the answers. Let us substitute all these answers in the correct solution. So the correct solution now reduces to C1 0. So C2 sin Px. In the place of P, substitute n pi by L. So C2 sin n pi by Lx into, in the second term, C3 is 0. C3 is 0. So you have only C4 sin P. In the place of P, we have to substitute n pi by L. So sin n pi at by L. Now, club this C2 into C4. Generally, you should write that as Cn. C2 into C4, we should generally write as Cn, and we have to allow n to take all the values from 1 to infinity. So C2 into C4, we have to write as Cn, and we have to put a summation n equal to 1 to infinity. So this is known as generalized solution or most general solution. Now let us apply the last boundary condition which is pending in this most general solution, because once we have generalized, this is the last current updated solution. So here we have to apply the last boundary condition, dou y by dou t at x equal to 0 equal to v. Now dou y by dou t we need. This is y. This is only y. So what is dou y by dou t? Differentiating y with respect to t. So when we differentiate y with respect to t, here you have t. Don't touch the x term. Just we have to differentiate the t term. So sin n pi at by L, when you differentiate, you get cos n pi at by L. So you can see here, sin when we differentiate cos into n pi a by L will come because you are differentiating with respect to t. Now this is dou y by dou t. But we need dou y by dou t at x comma 0. What's the meaning of x comma 0? Putting t 0. So dou y by dou t at x comma 0 means you have to put t 0 here. Where you have t, here you have t. So when you put t 0, cos 0 becomes 1. So you have this term. Cos 0 has become 1. So this is the term. And the condition says this is equal to v. Condition says this is equal to v. So substitute this is equal to v, which is a function of x. So we just call that as some f of x for simplicity. Now look at this. Cn n pi a by L, writing on the constants together, sin n pi x by L equal to f of x. So observe this. We have already studied this somewhere. Observe this term. Do you remember? Yes, half range sine series. Is it not half range sine series formula? Look at this formula of half range sine series. F of x equal to sigma bn sin n pi x by L, where bn has got a formula. Compare this and this. Exactly the same series here we have, but in the place of bn, here you have cn n pi a by L. So when we write bn formula, here in the place of bn, let us write the formula for bn, but in the place of bn, here you have cn n pi a by L. So taking and writing what is in the place of bn, cn n pi a by L, we have the formula for bn as 2 by L, 0 to L, f of x sin n pi x by L dx. Now let us substitute. Taking this n pi a by L immediately to the right side, you have 2 by n pi a into, substitute what is f of x. What is f of x? This function. So look at this f of x. In 0 to L by 2 it is cx. In L by 2 to L it is c into L minus x. So this integration 0 to L we have to split into 2. In 0 to L by 2 the function is f of x is cx. Then in L by 2 to L the function is c into L minus x. c into L minus x. So substitute. Splitting into 2 integrals. Now look at this. You know how to integrate this using Bernoulli's law. Keep the first, integrate the second, minus differentiate the first, integrate the second, plus differentiate the first, integrate the second. It goes like that. So let us apply the Bernoulli's law here. Look at the first integration, taking c out. First term is x. Keep the first, integrate the second. Sin when you integrate minus cos n pi x by L by n pi by L. Minus differentiate the first. X when you differentiate 1. Integrate the second. Cos when you integrate sine. So minus divided by again n pi by L will come. So n squared pi squared by L squared. This is from 0 to L by 2. Plus similarly integrate the second term. So keep the first L minus x into integrate the second. Sin when you integrate minus cos n pi x by L by n pi by L minus differentiate the first. So when you differentiate, you get So when you differentiate the first, you get minus 1 here, and integrate the second. Cos when you integrate, you get sine. And this we have to apply the limit from L by 2 to L, L by 2 to L. Now when you apply the limits, you will get terms like this: sine 0, 0, cos 0, 1, and sine n pi you will get, cos n pi you will get. These are the basic values you should remember. So when you substitute the limit for all these values, you will have terms like this. So you can see, substitute in the place of x L by 2, minus in the place of x 0. Similarly here you can substitute. So when you substitute, you will get values like this. And if you observe this term minus L by 2 cos n pi by 2 by n pi by L, here you have minus minus plus. So these two terms will be cancelled, and this term will be both sides positive. So it will be plus plus. So you will have the sin n pi by 2 term 2 times. So 2c by n pi a into 2 times of that. So this is the final answer of Cn. And this answer of Cn you have to substitute in the most general solution. So this is the most general solution we got. In the most general solution, substitute the answer of Cn. So you get like this. This is the ultimate answer of the displacement of the string. So using the concept whatever you have learnt, just try these two problems.